Hello dear students, welcome to the lecture 11 of Artificial Intelligence and Machine Learning course. So today at the part 1 we are going to see gradient descent.
Gradient descent.
Okay, so what is gradient descent?
Gradient descent is a first-order iterative optimization algorithm for finding the minimum of a function. To find a local minimum of a function using gradient descent, one takes steps proportional to the negative of the gradient or approximate gradient of the function at the current point.
Okay, it is really hard to understand just by the regular or mathematical definition of such methods. Therefore, let's try to find some more explanative example. Okay.
Gradient descent is an optimization algorithm used to minimize some function by iteratively moving in the direction of steepest descent as defined by the negative of the gradient. In machine learning, we use gradient descent to update the parameters of our model. Parameters refer to coefficients in linear regression and weights in neural networks. Introduction: consider the three-dimensional graph below in the context of a cost function. Our goal is to move from the mountain in the top right corner, high cost, to the dark blue sea in the bottom left, low cost. The arrows represent the direction of steepest descent, negative gradient, from any given point, the direction that decreases the cost function as quickly as possible.
Okay,
Source.
so this is more explanative. Let's try to find if there is a bigger picture. Okay, so the gradient descent for any given point is being these arrows. These are the steepest. What does steepest mean? It means that when we take these actions, we will get the lower area with maximum possible descent. And our aim is starting from this mountain top to getting to the lowest place. What does this mean in machine learning? It means that we want to minimize the cost function. Okay, so what is cost function and what is minimizing it? Okay, so let's look for that. One moment, I'm checking something. Okay, so cost functions, you see mean, difference, squared. Okay. Okay.
What is a cost function? In the case of gradient descent, the objective is to find a line of best fit for some given inputs, or x values, and any number of y values, or outputs. A cost function is defined as a function that maps an event or values of one or more variables onto a real number intuitively representing some cost associated with the event. In this situation, the event we are finding the cost of is the difference between estimated values, or the hypothesis, and the real values, the actual data we are trying to fit a line to. To state this more concretely, here is some data and a graph.
Okay, so we have x point 1, I point 1, x point 2, I 2.5, x is 3 point, and I is 3.5. So it is like this. And now,
Pretty boring graph. The goal here is to find a line of best fit, a line that approximates the values most accurately. Here are some random guesses.
okay, so here are random guesses. You see blue and best fit 2, best fit 3, and the original data. And they are like this. Best fit 1 is this one, best fit 2, best fit 3.
Making that beautiful table was really hard. I wish Medium supported tables. Anyway, we have three hypotheses, three potential sets of data that might represent a line of best fit. The slope for each line is as follows.
Okay, like this.
Best underscore fit underscore 2 looks pretty good, I guess. But we are data scientists, we don't guess, we conduct analysis and make well-founded statements using mathematics. Understanding the cost function, let's do an analysis using the squared error cost function.
Okay, so this is the squared error cost function. I minus I, and we square them, then we sum them, and then we divide them.
Remember, a cost function maps event or values of one or more variables onto a real number. In this case, the event we are finding the cost of is the difference between estimated values, or the difference between the hypothesis and the real values, the actual data we are trying to fit a line to. Let's unwrap the mess of Greek symbols above. On the far left, we have 1/2 m. M is the number of samples. In this case, we have 3 samples for x, those are 1, 2 and 3. So 1/2 m is a constant. It turns out to be 1/6, or 0.1667. Next we have a sigma. This means the sum. In this case, the sum from I to m, or 1 to 3. We repeat the calculation to the right of the sigma, that is, for each sample.
So xi minus I, and we take their square. I mean, we take their power of 2.
The actual calculation is just the hypothesis value for h, x, minus the actual value of y, then you square whatever you get. The final result will be a single number. We repeat this process for all the hypotheses, in this case best underscore fit underscore 1, best underscore fit underscore 2 and best underscore fit underscore 3. Whichever has the lowest result, or the lowest cost, is the best fit of the 3 hypotheses. Let's go ahead and see this in action to get a better intuition for what's happening. Calculating the cost function by hand, let's run through the calculation for best underscore fit underscore 1. We know the half a meter is simply 1/6, so we will focus on the summing the result of.
Because m is 3 here, because we have 3 data points, as you can see. Therefore, this is 1/6. And then
For best underscore fit underscore 1, where I equals 1, or the first sample, the hypothesis is 0.50. This is the h underscore the ha x I part, or what we think is the correct value. The actual value for the sample data is 1.00. So we are left with 0.50 to 1.00 squared, which is 0.25. Let's add this result to an array called results. The next sample is x equals 2. The hypothesis value is 1.00, and the actual y value is 2.50. So we get 1.00 to 2.50 squared, which is 2.25. Add it to results.
Okay, so results are like this, and then we continue for x3.
Lastly, for x equals 3, we get 1.50 to 3.50 squared, which is 4.00.
Okay, and so this is our results, and finally we add them all up and multiply them by 1/6.
Finally, we add them all up and multiply by 1/6.
Why? Because it is in the it is the formula. The formula is the cost function we are using. So this is our squared error cost function. This is a very generic cost function for linear separability. Okay, and the final result is being
6.5 asterisk 1/6 equals 1.083. The cost is 1.083. That's nice to know, but we need some more costs to compare it to. Go
so
ahead and repeat the same process for best underscore fit underscore 2 and best underscore fit underscore 3. I already did it, and I got.
so you see the best fit 1 and best fit 2 are no, the best one, the lowest one is best fit 2. Therefore the best fit 2, you see the orange one, is the best one that matches as much as the original data for separation.
A lowest cost is desirable. A low costs represents a smaller difference. By minimizing the cost, we are finding the best fit. Out of the three hypotheses presented, best underscore fit underscore 2 has the lowest cost. Reviewing the graph again.
Okay, so it is like this.
The orange line, best underscore fit underscore 2, is the best fit of the three. We can see this is likely the case by visual inspection, but now we have a more defined process for confirming our observations.
Okay.
Use with linear regression. We just tried three random hypotheses. It is entirely possible another one that we did not try has a lowest cost than best underscore fit underscore 2. This is where gradient descent, henceforth GD, comes in useful. We can use GD to find the minimized value automatically, without trying a bunch of hypotheses one by one. Using the cost function in conjunction with GD is called linear regression.
Okay, this is important. Okay, so then we can continue with this was the understanding calculation cost function, and this is the machine learning big one, cost function gradient descent. Okay, let's read this one as well because I think this is another good article that explains better.
Machine Learning Week 1, Cost Function, Gradient Descent and Univariate Linear Regression.
One moment.
Cost functions mean difference squared gradient descent linear regression.
Okay.
Model representation first. The goal of most machine learning algorithms is to construct a model, a hypothesis that can be used to estimate y based on x. The hypothesis, or model, maps inputs to outputs. So, for example, say I train a model based on a bunch of housing data that includes the size of the house and the sale price. By training a model, I can give you an estimate on how much you can sell your house for based on its size. This is an example of a regression problem. Given some input, we want to predict a continuous output. This is an example of a regression problem. Given some input, we want to predict a continuous output.
Okay, when you want to predict a continuous output, it is a regression problem. Okay, this is important for you to understand.
The hypothesis is usually presented as
Okay, h0x equal to theta, h theta x equal to theta 0 plus theta 1x and such.
the theta values are the parameters. Some quick examples of how we visualize the hypothesis.
Okay, so if theta 0 is 1.5 and theta 1 is 0,
This yields x equals 1.5 plus 0x. 0x means no slope, and y will always be the constant 1.5. This
So-
looks like.
so it looks like this because we have no slope and it is always 1.5 no matter what the x is. Okay. However, theta 0 is 1 and theta 1 is 0.5. So it becomes like this.
Hx equals 1 plus 0.5x.
So it is like this, as you can see. This is the slope.
The goal of creating a model is to choose parameters, or theta values, so that hx is close to y for the training data, x and y, so for this data.
Okay. So let's say we have this as data points. X is
X equals 1, 1, 2, 3, 4, 3, 4, 6, 4.
okay, and
Y equals 2, 1, 0.5, 1, 3, 3, 2, 5, 4.
okay, so they are displayed on the X and Y space like this. So we will try to
I will try and find a line of best fit using linear regression. Let's get started.
So the fit will be for um, let's say, what can we say? We will try to find a drawing or line that will match these data points as much as possible. So we will try to reduce the cost of the function, as we have just seen in the previous article.
Cost function. We need a function that will minimize the parameters over our dataset. One common function that is often used is mean squared error, which measure the difference between the estimator, the dataset, and the estimated value, the prediction.
Okay.
It looks like this.
So this is the mean squared error. So this function is mean squared error. Okay.
Mean squared error.
You may use different functions as well. It is totally up to you.
It turns out we can adjust the equation a little to make the calculation down the track a little more simple. We end up with.
So it can be also defined like this. Okay.
Let's apply this const function to the follow data.
Okay.
For now, we will calculate some theta values and plot the cost function by hand. Since this function passes through 0, 0, we are only looking at a single value of theta. From here on out, I'll refer to the cost function as j. Theta. For j1, we get 0. No surprise, a value of j1 yields a straight line that fits the data perfectly. How about j 0.5?
So you say this is j.1 and this is j 0.5.
The MSE function gives us a value of 0.58. Let's plot both our values so far. j1 equals 0, j 0.5 equals 0.58.
So MSA is the mean squared error function. So it will be like this and like this.
We can see that the cost function is at a minimum when theta equals 1. This makes sense. Our initial data is a straight line with a slope of 1, the orange line in the figure above.
Okay.
Gradient descent. We minimized j/th by trial and error above, just trying lots of values and visually inspecting the resulting graph. There must be a better way? Q gradient descent. Gradient descent is a general function for minimizing a function, in this case the mean squared error cost function.
Okay, so this is important. Let's read again.
Gradient descent is a general function for minimizing a function, in this case the mean squared error cost function.
So gradient descent is a general function and it tries to minimize the function you are using for your calculation. It can be mean squared error or it can be other functions, for example. Let's check the alternatives. Okay. You see performance functions, alternatives of mean squared error for neural network learning. So they have studied and published an article. And let's see. Okay. So there are mean absolute error also, root mean squared error, and no other ones. You can also see other metrics. You see how to use metrics for deep learning. You can use other metrics as well. It is not the topic right now.
Gradient descent basically just does what we were doing by hand, change the theta values, or parameters, bit by bit, until we hopefully arrived a minimum.
So you see gradient descent changes our parameters bit by bit. This is what does it do in every algorithm you use gradient descent.
We start by initializing theta 0 and theta 1 to any two values, say 0 for both, and go from there. Formally, the algorithm is as follows.
So this is the gradient descent algorithm. Let's try to understand it.
Where alpha is the learning rate, or how quickly we want to move towards the minimum. If alpha is too large, however, we can overshoot.
So this alpha is the learning rate. And there is, we have, I don't know what is this. I am really bad at reading mathematical functions, seriously. And there is theta, as we can see. So let's try to understand gradient descent visualization. We have initial weight, and from here we take the steps to find global cost minimum, and it happens here. So what does gradient function do for us is, based on the gradient, you see we can calculate the gradient like this. We take steps to lower our cost.
Bringing it all together, linear regression quickly summarizing, we have a hypothesis.
Okay, so our hypothesis is like this,
which we need fit to our training data. We can use a cost function such mean squared error.
Okay, one moment. Okay, all right. And so,
which we need fit to our training data. We can use a cost function such mean squared error,
like this,
which we can minimize using gradient descent.
So you see, G is between 0 and 1. Okay.
Which leads us to our first machine learning algorithm, linear regression. The last piece of the puzzle we need to solve to have a working linear regression model is the partial derivative of the cost function.
So this is the partial derivative.
Partial derivative of the cost function which we need to calculate. Which turns out to be.
So the partial derivative of the cost function is calculated like this.
Which gives us linear regression.
And repeat until convergence, as you can see.
With the theory out of the way, I'll go on to implement this logic in Python in the next post.
Okay, so we have theta 0 and theta 1, and the difference between theta 0 and theta 1 is theta 1 is equal to theta 1 minus this one. Let's look at this. Okay, so we multiply it with the new x value, and then we take the partial derivative of this version. Okay, it is more about mathematics, but now we get the idea of cost function, which was my aim. So let's read this again.
What is gradient descent? Gradient descent is a first-order iterative optimization algorithm for finding the minimum of a function. To find a local minimum of a function using gradient descent, one takes steps proportional to the negative of the gradient or approximate gradient of the function at the current point.
All right, then let's continue.
Linear models. A strong high-bias assumption is linear separability, in two dimensions, can separate classes by a line in higher dimensions, need hyperplanes. A linear model is a model that assumes the data is linearly separable. A linear model in n-dimensional space, i.e. n features, is defined by n plus 1 weights.
So if we have n features, our model is in n-dimensional space, and we have n plus 1 weights. For example, we are classifying apples and oranges, and we are taking into consideration their weight, their color, their shape. That makes 3 features. Therefore, our model would be 3-dimensional space, and we would have 4 weights. If we add this to this model, for example, we can add whether has leaves or not, for example, leaf. That makes it 4-dimensional and 4 features. So you get the idea. Okay. In 2 dimensions, a line is defined as W1 multiply with F1 plus W2 dot F2 plus B, and where B equals to minus A. So you see, this is weight 1, this is the feature 1, this is weight 2, feature 2, and some parameter. In 3 dimensions, it becomes weight 1, feature 1, weight 2, feature 2, weight 3, feature 3, and plus B. And in m dimensions, a hyperplane. You see, m dimensions, it is called as hyperplane. It is like this: sum of all weights multiplying with their corresponding feature plus B. Okay.
Perceptron learning algorithm. Repeat until convergence, or for some hash of iterations, for each training example f1, f2, fm, label, if prediction asterisk label is less than or equal to 0, they don't agree for each wj, wj equals wj plus fj asterisk label b equals b plus label prediction equals b plus wj fj.
Okay, we have seen already the perceptron learning algorithm. So which line will it find? It can find any of these lines based on the algorithm we are using. Only guaranteed to find some line that separates the data. Okay. So linear models are...
Perceptron algorithm is one example of a linear classifier. Many other algorithms that learn a line, i.e. a setting of a linear combination of weights, goals, explore a number of linear training algorithms, understand why these algorithms work.
Okay. So you see, if our prediction is wrong, in perceptron algorithm B, change the weight according to our prediction direction. If we have made negative prediction, we change according to that. If we made positive prediction, we change according to that. We have seen that. You see, if it didn't contribute but could have, we decrease the value. If it contributed in the wrong direction, we decrease the value. And we have seen that in the previous lecture, so I'm not going to explain it again. Okay, model-based machine learning. Pick a model, e.g. hyperplane, a decision tree. A model is defined by collection of parameters. What are the parameters for decision tree or perceptron? And pick a criteria to optimize as known as objective function. What criterion to do decision tree learning and perceptron learning optimize? Develop a learning algorithm. The algorithm should try and minimize the criteria, sometimes in a heuristic way, non-optimally. You see criteria as being our cost function, sometimes explicitly. So these are the parameters we want to learn. Okay, B and W weights. Pick a criteria to optimize. Some notation of the indicator function, if true 1, if not false. Okay, some notation dot product. Sometimes it is convenient to use vector notation. Yes, we usually use that. We present an example f1, f2 until fm as a single vector x. Similarly, we can represent the weight vector as like this. The dot product between two vectors and b is defined as like this. Okay, what does this equation say? Anyway, we don't need that. So loss function is totally up to us, but usually it is used. The used one is mean squared error, distance from hyperplane, and we would like to reduce the distance from hyperplane. Whether or not prediction label agree, incorrect, total number of mistakes. Okay, find a b and w and p such that minimize the loss function. Or how do we do that? How do we do the minimize the loss function? So let's assume this is our loss and this is our results based on the each w. Oh,
Each time we change W such that the example is right, wrong, the loss will increase, decrease.
okay.
Find W and B that minimize the 0/1 loss.
So this is NP hard problem. What is NP hard? Let's also give you the basic idea about NP hardness.
In computational complexity theory, NP hardness, non-deterministic polynomial time hardness, is the defining property of a class of problems that are informally at least as hard as the hardest problems in NP. A simple example of an NP hard problem is the subset sum problem. A more precise specification is, a problem H is NP hard when every problem L in NP can be reduced in polynomial time to H, that is, assuming a solution for H takes 1 unit time, H's solution can be used to solve L in polynomial time, 1, 2. As a consequence, finding a polynomial time algorithm to solve any NP hard problem would give polynomial time algorithms for all the problems in NP. As it is suspected that P NEQ NP, it is unlikely that such an algorithm exists. 3. A common misconception is that the NP in NP hard stands for non-polynomial, when in fact it stands for non-deterministic polynomial acceptable problems. 4. It is suspected that there are no polynomial time algorithms for NP hard problems, but that has not been proven. 5. Moreover, the class P, in which all problems can be solved in polynomial time, is contained in the NP class. 6.
Okay, so if the algorithm is not P, it is extremely hard to solve within a given time. You may look for more information.
Challenge. Small changes in any W can have large changes in the loss. The change isn't continuous. There can be many local minima at any give point. We don't have much information to direct us towards any minima.
Okay, so more manageable loss function. Okay, you see loss decreases by W and increases.
Ideally, continues, i.e. differentiable, so we get an indication of direction of minimization, only one minima.
So this is ideal loss function because we know the direction of loss and we have only one local minima. Here you see we have two local minimas like here and here, and this doesn't have one direction. It goes down, it goes up, it goes down, it goes up. So convex functions are what we want because they have single local minima and we know the direction.
One definition, the line segment between any 2 points on the function is above the function.
Okay. Okay, surrogate loss functions.
For many applications, we really would like to minimize the 0/1 loss. A surrogate loss function is a loss function that provides an upper bound on the actual loss function, in this case, 0/1. We'd like to identify convex surrogate loss functions to make them easier to minimize. Key to a loss function is how it scores the difference between the actual label y and the predicted label y.
Okay, so this is important. Let's repeat.
Key to a loss function is how it scores the difference between the actual label y and the predicted label y.
So our aim is predicting the label correctly with minimal difference. So how we calculate the difference makes impact. Okay, so let's look for a surrogate loss function. Okay. You see, these are all mathematical functions and really hard to understand unless you spend quite a bit time and have good mathematics. Okay, let's read this.
On a very general note, this function is used to penalize the misclassifications. In the end, your aim is to classify the data in correct classes and to evaluate your results. To train the model, you develop the loss functions and most frequently mean squared error. But in MSE, the accuracy may not reflect the true accuracy of the classifier. So we would like a loss function, like 0/1 loss function, which gives error as 1 if the class is wrong and 0 if the prediction is right. This is used in SVM and called as Hinge loss. But in broader terms, if you look at the formula,
Okay, so here we penalize misclassification as well, not just we calculate such as the distance. Okay. Okay, it is really long. Let's continue. So the surrogate loss function. You see hinge, exponential, squared loss. Okay, why do these work? What do they penalize? Okay, 0/1 is the regular loss function, mean squared error, or 0 loss is whether it is loss or not, I think. So there is squared error, max, hinge, and exponential. Okay, this is how they are penalized, or yeah, this is how they are penalized. So the orange is hinge. Okay, finding the minimum.
you're blindfolded, but you can see out of the bottom of the blindfold to the ground right by your feet. I drop you off somewhere and tell you that you're in a convex-shaped valley and escape is at the bottom, minimum. How do you get out?
Okay, how do we get out from this function? One approach, gradient descent.
Partial derivatives give us the slope, i.e. direction to move, in that dimension.
You see, partial derivatives is the key. Actually, you need to understand this if you want to develop a new algorithm or improve an existing algorithm, and they are more likely thesis of a degree thesis or PhD degree thesis. But just having a basic idea is not harmful and would help you. Okay, let's read this article.
A quick introduction to derivatives for machine learning people. Introduction. If you're like me, you probably have used derivatives for a huge part of your life and learned a few rules on how they work and behave without actually understanding where it all comes from. As kids, we learn some of these rules early on, like the power rule, for example, in which we know that the derivative of x squared is 2x, which in a more general form turns to dx equals x. This is in principle fine, since all rules can be readily memorized and looked up in a table. The downside of that is, of course, that you're using a system and a formalism that you fundamentally do not understand. Again, not necessarily an issue if you are not developing machine learning frameworks yourself on a daily basis, but nevertheless it's really nice to know what's going on behind the scenes. I myself despise black boxes, black medium square. So in order to dig a little bit deeper into that, I'll show you what it's all based on. To do that, we have to define what a derivative is supposed to do for you. Do you know? I'm sure you do, but just in case you don't. A derivative is a continuous description of how a function changes with small changes in one or multiple variables. We're going to look into many aspects of that statement. For example, what does small mean? What does change mean? Why is it continuous? How is this useful?
Okay.
The total and the partial derivative, these terms are typically a source of confusion for many, as they are sometimes seen as equivalent and in many cases they seem indistinguishable from one another. They are, however, not. Let's start by defining the partial derivative and then move on to the total derivative from there. For this purpose, I will use an imaginary function f, t, x, y, where we have three variables t, x, and y. The partial derivative answers the questions of how f changes f when one variable changes by a small amount x. In this setting, all other variables are assumed to be constant and static. Thus the partial derivative is denoted f(x). In order to show what happens when we do this operation, we need to first define f as something. Let's say it looks like this: f t x y equals txy 4 pi 3, which incidentally is the volume of an ellipsoid. Well, perhaps not so incidentally. Either way, I have chosen a different parametrization than is commonly used. In the picture below, you can see from top to left to right a sphere, spheroid, and ellipsoid respectively. In our setting, we can choose t equals a, x equals b, y equals c for the dimensions.
Okay.
The partial derivative of the volume of these geometrical spaces then becomes f x equals 4 pi 3 ti, where we have applied the power rule. As you see, the t and the y was not touched since we assumed them to be fixed. Thus in the picture above we model what happens with the volume as b extends or shortens by a small amount. This answers our question if they are really independent of x, but what if they are not? Well, in this case we need the total derivative of f with respect to x, which is denoted by df dx and is defined like this.
Okay.
Where you can see the partial derivative as a part of the total one. So for illustrative purposes, let's constrain the function to a situation where t equals x. What happens with the derivative then? Well, the partial derivative from before stays the same. But the two other terms we need to calculate. The first part becomes f t dt dx equals 4 pi 3xy1, while the last part turns to
Okay. I think let's continue reading from here.
Building your own backpropagation engine for deep neural networks. In this section I'll take you through a simple multi-layered perceptron and a derivation of the backpropagation algorithm. There are many ways to derive this, but I'll start from the error minimization approach, which basically describes the fit of a neural network f, x, theta, by the deviance from a known target y. The architecture we will solve for is shown in the image below, where we have two hidden layers. We stick to this for simplicity. We'll also only use one output instead of multiple, but it's readily generalizable. Instead of representing our network graphically, we'll do a more formal representation here, where the functional form will be stated mathematically. Basically, the functional form will be where the bold face symbols denotes vectors. The phi s equals 1 plus express as. Function is the sigmoid activation function with a hyperparameter a, which we will not tune or care about in this introduction. A small note here: disregarding the a parameter here is really silly, since it will fundamentally change the learning of this network. The only reason I allow myself to do it is because it's beyond the scope to cover it at this point. In order to train a neural network, we need to update the parameters according to how much they affect the error we see. This error can be defined like this for a regression-like problem for a data point x, y.
Okay, so you see, f x t theta is the thing we predict, and it is the yt is the real value. Then we take their power 2, then we divide them by 2, and this is the error rule we are using in this case.
If we look at the second last layer, then we simply update the parameters according to the following rule.
So you see the new theta gk equal to theta old gk subtraction with this formula.
For each new data point. This is called stochastic gradient descent, SGD. You can read a lot about that in many places, so I won't dive into it here. Suffice it to say that this process can be repeated for each parameter in each layer. So the infamous backpropagation algorithm is just an application of updating your parameters by the partial derivative of the error with respect to that very parameter. Do the partial derivatives for yourself now and see how easy you can derive it. A small trick you can use is to realize that phi s equals phi s1 phi s, where I've used the prime notation for a derivative. There's a nice tutorial on how to do this numerically here.
Okay.
Take-home messages: the total derivative and the partial derivative are related, but at times fundamentally different. All constraints and variable substitutions have to be done before calculating the partial derivative. The partial derivative ignores implicit dependencies. The total derivative takes all dependencies into account. Many magic recipes, like the backpropagation algorithm, usually comes from quite simple ideas, and doing it for yourself is really instructional and useful.
Okay, let's continue.
One approach: gradient descent. Partial derivatives give us the slope, i.e. direction to move, in that dimension approach. Pick a starting point, w, repeat, pick a dimension, move a small amount in that dimension towards decreasing loss using the derivative.
Okay. You see starting point, and with steps we move to the minima.
Pick a starting point, w, repeat until loss doesn't decrease in all dimensions. Pick a dimension, move a small amount in that dimension towards decreasing loss using the derivative. Wj equals wjh dd wj loss. W, what does this do?
Okay.
Learning rate, how much we want to move in the error direction, often this will change over time.
Okay, there are some other mathematics behind the scenes. Okay, exponential update rule. These are all related to mathematics. If you want to develop or tune an algorithm, you have to become expert on mathematics usually. Okay. In this lecture, I just want you to have basic idea about how they are done and how can you use them to solve real life problems. Okay.
If they're the same sign, as the predicted gets larger, their update gets smaller. If they're different, the more different they are, the bigger the update.
Okay. One concern. Okay, this is important.
Note, for gradient descent, we always update.
If we are using the gradient descent, we always update, not just we update if the prediction is incorrect.
We're calculating this on the training set. We still need to be careful about overfitting. The min W(b) on the training set is generally not the min for the test set. How did we deal with this for the perceptron algorithm?
Okay, how can we deal with this for the perceptron algorithm? Let's make some brainstorm. How can we deal that? We can use unfold cross-validation. That is how we can deal with that, or we can separate our training data as to two parts. And first we start with full data, then we split it to test data and training data, and then we split training data to train and test data. And at each training we can check the test data, or we can use unfold cross validation. So it is about that. So the summary.
Summary model-based machine learning. Define a model, objective function, i.e. loss function, minimization algorithm, gradient descent minimization algorithm, require that our loss function is convex, make small updates towards lower losses. Perceptron learning algorithm, gradient descent, exponential loss function, modulo learning rate.
All right, let's start part 2, regularization.
Regularization. Overfitting revisited, regularization. A regularizer is an additional criteria to the loss function to make sure that we don't overfit. It's called a regularizer since it tries to keep the parameters more normal, regular. It is a bias on the model, forces the learning to prefer certain types of weights over others. Should we allow all possible weights? Any preferences? What makes for a simpler model for a linear model? Generally, we don't want huge weights if weights are large. A small change in a feature can result in a large change in the prediction. Also gives too much weight to any one feature. Might also prefer weights of 0 for features that aren't useful. How do we encourage small weights? Or penalize large weights?
So this is about this, as you can see, and also we prevent large value having weights to break our algorithm. So how do we encourage small weights or penalize large weights with regularizer? Common regularizers are sum of weights and sum squared weights. We have seen them, if you remember.
Squared weights penalizes large values more. Sum of weights will penalize small values more.
Okay, so you see sum of base 1 norm and sum of squared base 2 norm.
Smaller values of p less than 2, encourage sparser vectors. Larger values of p discourage large weights more.
Okay, there are p normalizations, p1, p2, p3, you see, and all p norms penalize large weights. P smaller than 2 tends to create sparse, a loss of 0 weights. P bigger than 2 tends to like similar weights. Okay, I'm trying to find good information here. Okay.
Loss function penalizes examples where the prediction is different than the label. Regularizer penalizes large weights. Key, this function is convex, allowing us to use gradient descent.
Okay. You see, it is all about mathematics. These algorithms are usually found by mathematicians. Okay, so these are important L1 regularization, and there are L2 regularization and LP regularization. Because these regularizations heavily affects your performance. Okay, I have tested these regularizations in my thesis. Let's open my thesis. Um, okay, it is available on. Let's open it from here. I think it doesn't show here. What was its name? I can't remember. One moment. We had a link somewhere here, but okay. Okay, D space. Okay, now I have remembered. Sorry about the delay. Okay, here. And I have uploaded my thesis to here. Okay, here. Let's download and open it. Oh, this is not a thesis. Yeah, this is not a thesis. Sorry about. Okay, let's open this. Hmm. I remember I have done this, but okay, you see.
More information about these parameters can be obtained from the official document 50 of libsvm framework. In addition to these parameters, we have tested L1, L2, L3, L4 and L5 vector normalizations 51 of SVM nodes provided by libsvm sharp wrapper. For
Okay,
document vector computation, we have tested the following metrics.
okay, let's see the regularization results. You see they are presented under normalization, and we have found that the best results are obtained by L2. Okay, so it makes difference. However, based on the distance or similarity metrics you are using, it may change. For example, when I used BM25 and IDF Smooth, no normalization did the best. However, when we have used the log normalization for term frequency and probabilistic inverse document inverse document frequency, L2 has resulted in the best performance. So this is important, the regularization and normalization. You see, this is how they are in mathematical terms.
Regularizers summarized. L1 is popular because it tends to result in sparse solutions, i.e. lots of zero weights. However, it is not differentiable, so it only works for gradient descent solvers. L2 is also popular because for some loss functions, it can be solved directly, no gradient descent required, though often iterative solvers still. LP is less popular since they don't tend to shrink the weights enough.
Okay, there are other loss functions without regularization. The generic update is like this. And many tools support these different combinations. You can look for Surrogate learning package. You see stochastic gradient descent. Let's read it.
Stochastic gradient descent (SGD) is a simple yet very efficient approach to fitting linear classifiers and regressors under convex loss functions such as linear, support vector machines and logistic regression. Even though SGD has been around in the machine learning community for a long time, it has received a considerable amount of attention just recently in the context of large-scale learning. SGD has been successfully applied to large-scale and sparse machine learning problems often encountered in text classification and natural language processing. Given that the data is sparse, the classifiers in this module easily scale to problems with more than 10 to the power of 5 training examples and more than 10 to the power of 5 features. Strictly speaking, SGD is merely an optimization technique and does not correspond to a specific family of machine learning models. It is only a way to train a model. Often, an instance of SGD classifier or SGD regressor will have an equivalent estimator in the scikit-learn API, potentially using a different optimization technique. For example, using SGD classifier, loss equals log, results in logistic regression, i.e. a model equivalent to logistic regression which is fitted via SGD instead of being fitted by one of the other solvers in logistic regression. Similarly, SGD regressor, loss equals squared underscore loss, penalty equals L2, and ridge solve the same optimization problem via different means.
Okay.
The advantages of stochastic gradient descent are efficiency, ease of implementation, lots of opportunities for code tuning. The disadvantages of stochastic gradient descent include SGD requires a number of hyperparameters such as the regularization parameter and the number of iterations. SGD is sensitive to feature scaling.
Okay. So here you see sparse data, and let's learn that as well.
For the ease of understanding, I'll describe this using an example. Let's say that you are collecting data from a device which has 12 sensors. And you have collected data for 10 days. The data you have collected is as follows. This is called sparse data because most of the sensor outputs are zero. Which means those sensors are functioning properly but the actual reading is zero. Although this matrix has high dimensional data, 12 axes, it can be said that it contains less information.
So this data set is 12 dimensional because it has 12 features, and
let's say two sensors of your device is malfunctioning. Then your data will be like. In this case, you can see that you cannot use data from sensor 1 and sensor 6. Either you have to fill data manually without affecting the results or you have to redo the experiment.
okay, so this is sparse data and the other one is missing data. Okay. All right, I think it is enough for this week. If you haven't decided your project yet, please let me know what you are going to do. And please already start your project. You see, in this lecture we have seen lots of mathematics. I don't expect you to learn and understand these mathematical functions because I know that they are really hard, and I just need you to have some basic information. You should always use open frameworks when doing such functions, because even if you code yourself, you are likely to make errors, mistakes, unless you want to improve an algorithm or develop a new algorithm. It is not necessary. You should use ready frameworks. Okay, I think this is enough for this week. Okay, hopefully see you next week. End of lecture.